Okay, so last week we didn't talk about Markov chains, but we talked about bases and change of bases. And then at the very end of the lesson, we talked about these change of basis matrices. And then the next section that we would cover is application of Markov chains, or just Markov chains, which Markov chains are primarily used in statistics, where you have a matrix, or what's called a stochastic matrix, that models some type of situation um, that you can put an initial state vector or a probability vector into that to multiply it to that matrix, and it gives you an output. And then by repeatedly doing this again and again and again, by multiplying by that matrix, you will find a current state, after so many iterations of the multiplication. So I figured we would look at one example from this section just to get a good understanding of what that section is talking about. You might remember from the first chapter, when we were still together in school, we talked about this migration matrix from a city to suburb. I even put it on our first test, and we called this matrix M, and we wrote it something like this. And so this is just these are probability vectors, or you could say a distribution vector, that's modeling. Notice that this column adds up to 100%. So it's a total of city population, and this column would be the total suburb population. So this would be the migration matrix. Well, it's also called a stochastic matrix. It's modeling some type of distribution of people. So what we want to do is multiply this to the initial state vector, x0, which is 600,000 people in the city and 400,000 people in the suburbs. Now I've already got this problem pre-baked here into my calculator. I took the time to put it in. So right here is the matrix M, and I've already got our matrix B. So this is the migration matrix. So what we want to do is take A, and we'll I think I have to go up and select A, and then take B. We'll multiply these two together, and this will give me the next year's population distribution. So in the next year, we'll have 582,000 in city and 418,000 in the suburb. So this distribution will change year after year, and provided that this migration matrix stays the same, or that the tendency of migration stays the same, then you can find a pattern or a sequence of population for the future. I think we even did something like this in class. So what we want to do now is apply the migration matrix to the new distribution of city-suburb. So I'm going to take, whoops, I want matrix A here, and apply it to this answer. And then apply it one more time. So this would be the distribution in the next year. And then if I just hit second enter, or just enter, I can keep getting the next years. So I can keep doing this for years and years and years. And what we'll notice, if I keep doing this long enough and mash the button, this is years. A way that we could do this a little bit quicker is we could say, hey, how about we take 30 A's, 30 migration matrices, and multiply them all at once to that answer. So there we go. And you can see that it's converging pretty quickly to this number. And so at some point, my calculator can't calculate the precision anymore. And so the number gets so close to this distribution. Well, this distribution is called a steady state vector. So steady state vector. And it's the distribution that if you apply that distribution, so it is 375,000 in the city and 625,000 in the suburb. So if you apply this distribution vector to the migration matrix, nothing changes. So this is called a steady state vector. So we're interested in finding these. Markov chains are very common, and so we would like to know how to find that steady state vector, which is what brings us to the next chapter on eigenvalues and eigenvectors. So that was my introduction to eigenvalues and eigenvectors. So this is the goal. Let me restate it slightly differently here. If you take a matrix, so this is like our migration matrix, this is the initial state, and you apply it to this, we want to know what if we just get x back, or better yet, what if this matrix just scales x? So I'm using lambda here as a scalar. Lambda is a Greek. We saw lambda with, we've used the variable before when we were talking about, oh boy, I have to go back to multi. What was the, oh boy, you might have to help me in the chat. See how well you remember your multivariable for some reason. Lagrange multipliers, thank you. You guys, man, you're on top of it. Look at that. Very good. Yes, so we use Lagrange multipliers. We use the scalar lambda. So lambda is often used as a scalar value. So here, we're going to use lambda to just represent a scale of this x. So what's happening is we're applying this matrix, which a matrix is just a transformation. So a matrix is nothing more than a transformation, which it might change the direction of a vector. It might stretch it. It might change its direction entirely into a different direction. So we're interested in when the matrix, what vector does the matrix only stretch it? So this is just a scale, S-C-A-L-E, or a stretch of the vector. So this is what we want, because that's the same type of idea as a steady state vector. So x would be called a steady state here. So that's what we're looking for. We want to find it. So we're going to call it, though, we're going to call that vector that happens to only be stretched by the transformation. We're going to call it an eigenvector. And then we'll call the lambda value that it's stretched by, we're going to call that an eigenvalue. So you might have heard of an eigenvector and an eigenvalue before. A lot of times they like to throw eigenvalue and eigenvector out in movies to make it seem like they're talking about something fancy. And we're going to pull the wool off their eyes here to reveal what eigenvalues and eigenvectors are. They're nothing very complicated. It's pretty much a common idea of just stretching some type of vector by a scalar is really all you're doing. And the key here, so why are we so interested in this, is that it is tied to a matrix. So we can talk about the eigenvector and eigenvalue of a matrix given any matrix. So even if you're not talking about a Markov chain, you could just take a matrix and then find its eigenvalues and eigenvectors. And so it's these vectors are tied to the matrix, and these real values, the scalar values, are tied to the matrix. They're unique to the matrix. So that's a very interesting thing. We're trying to uncover what matrices are all about, and this is going to help us. Okay. So let's see, do we want to go ahead and jump in? So maybe what I'll do here is write, so this is the equation that we want to deal with. Ax equals lambda x. And if we want to solve for the vector here, then let's subtract the lambda x to the other side. That leaves me with 0 on the other side. And then we'll factor out on the right-hand side. Remember, everything is side dependent here because we're dealing with matrices. We'll factor out the x. So it's x on the right. And so what that's going to leave here, we can't just write lambda because we need a vector placeholder. And so we're going to put the identity here. So when you factor out the x, it's like leaving a 1 behind, but it's a vector placeholder. And then x There we go. So we factored out x on the right-hand side, and now we want solutions to this equation. This is a homogeneous equation. Okay, so the solutions to this equation will actually be the eigenvectors. And so this is what we are interested in. So this is the definition here. So all non-trivial solutions, eigenvectors are non-zero vectors. So we're looking for non-trivial solutions to this equation. And let's see, what else do they say here? All set of all solutions to this equation is the null space of this. So null, if we take the null space of this, this is the set of all possible solutions, or the set of all possible eigenvectors. And so we call this set the eigenspace tied to a matrix, tied to the matrix A. Okay, maybe I'm getting a little bit ahead of myself. Let's go ahead and look at the first example. We might have to go back and look at those definitions, but I want to go ahead and get our hands on some problems here. So example 1, they give us a matrix, they give us two vectors, and then they say graph the images of u and v under the multiplication by a. So let's go ahead and take a product of a with u. It's going to be 3, 1. This is a negative 2, 0. And here's u. That's going to give me negative 5 and negative 1. And then we'll do the same for v. So here's a, and here's v. Take the product. 6 minus 2 is 4, 2. Okay, so let's plot them. The way that I'm going to plot these is I will plot the u in blue. So it's going to look like this. The original vector u was 1 to the left and up 1. So this is u. And then I'll do a of u in a different color. It's going to be, let's switch colors to maybe like purple, something like that. So it's negative 5 and then down 1. So this is AU, the image of U underneath A. Now we'll try the same for V. V goes to the right 2 and up 1. This is V. And then the image of U, let's do it in a darker green, is to the right 4 and up 2. Okay, so this is the image of V under A. So which of these two is an eigenvector of the matrix A? So is U or V an eigenvector? Aha, yeah, V. Very good. So V is an eigenvector because it is stretched. So what would the corresponding eigenvalue be? So V is an eigenvector. Good, Daniel. 2, and the reason that the eigenvector is 2, you're right, is because it is scaled by a factor of 2. It's stretched by 2. So we can write the equation AV equals 2V. So this is lambda, that's the eigenvalue, and V is the eigenvector. Very good. Cool. So U is not an eigenvector because it's not stretched. Its image is not stretched in the same direction. So it has to be in the same direction in order to be considered an eigenvector. So hopefully that's kind of a good visual representation of eigenvalue, eigenvector. And in fact, I think this is a good time that I can show you a little animation. Hopefully this plays well. Let me see. Where do I find it? I need to go here. I don't know if it'll play very well on my screen here, but we'll see. We want eigenvectors. There we go. So here we have a bunch of vectors, and then a transformation is applied. And you can see which of these vectors are eigenvectors. Look closely. Watch it transform. So the blue and the pink vectors are eigenvectors. So the blue and the pink would be eigenvectors. The red ones are not eigenvectors. So what would the eigenvalue of the pink vectors be? Or the purple vectors, whatever color that is. That's right, Glenn. It would be 1 because they're not stretched at all, right? They're the same size. Approximately, what do you think the other eigenvector would be for blue? What would the eigenvalue be for the blue ones? Yeah, probably 2. I don't think it could be 3. It stretches quite a bit, but I don't know. It's probably 2 or 3, something like that. But yeah, that's a pretty good little image. Here's another one. This one's the only difference here is the transformation is slightly different. I think it's transforming from all quadrants. So you can see here that no matter where the vectors originate, their scaling is dependent on the transformation itself. So it's just the same transformation, I think, but just in a different quadrant. You can see it taking place in other quadrants. Okay, so let's try another example here. So here it says, are U and V eigenvectors of A? If so, what are their eigenvalues? So it's the same process as before. So we want to do AU. Okay, let's take the product. We're going to get 6 minus 30, or negative 24. And then 30 minus 10, 20. Yeah. So what do you think? Is this an eigenvector of the matrix A? Is U an eigenvector, yes or no? Yeah, you're right, Justin. It is an eigenvector, and let's find its eigenvalue. Maybe I'll have you type it in. Anybody have an idea? Yeah, good, Caroline. It is negative 4. So it's stretched by a factor of negative 4. Now let's try V to see if it's an eigenvector. Okay, take the product here. That's going to be 6 minus 12, negative 6. 15 minus 4, or 11? Double check that. Yeah. So this is not equal to a multiple of V. We can tell because this is 11. 11 is fairly prime. So we'll say U is an eigenvector with eigenvalue lambda equal negative 4. And then we'll say V is not an eigenvector. Okay. The next example says, show that 7 is an eigenvalue for the matrix A in example 2. Find its corresponding eigenvector. So what they are saying to me is that there exists some vector out there. I'll call it, I need to use some other letter. Maybe I'll use W. So there's some other vector out there who, when multiplied by this matrix, it scales by 7 because that's its eigenvalue. So let's see if we can find it. So what we want to do is use that matrix A. It was 1, 6, 5, 2. And we don't know what W is, so we could say W1, W2 is equal to 7, W1, W2, or you could just write W there. So what we want to do is subtract the 7W. Let's just put W here instead. I think I'm getting ahead of myself in doing that, so we'll just write W. We'll subtract the 7W to the left-hand side. And then factor out the W on, we'll factor out the W on the right-hand side. So this leaves 7 times the identity matrix. We'll just use big parentheses. So we want to find the solutions to this equation. So let's write it a little bit more simply. Minus the identity 7007 x equals 0. Well, this is the same thing as saying negative 665 negative 5 augmented with 0, and then we want to row reduce, so let's divide each one of these rows by 6 and 5 respectively. We'll do negative 6, so we get 1, negative 1, 0, and then we get 1, negative 1, 0. And then we can subtract the top row from the bottom row. Okay, and now we have one free variable. So this column right here corresponds to W1, and this corresponds to W2. So my W vector looks like this, W1, W2, and W2 is a free variable, so we can write W1 in terms of W2. So let's add the W2 to the other side, and so you get 1 W2 is W1, and then W2 is free itself. And so we get the vector 1, 1, W2. So just like that. So here, this is the eigenvector. Let's test it. So let's take the matrix A, and we'll multiply the vector 1, 1. And we would expect 7 times 1, 1. So here's the matrix A. And we'll multiply 1, 1. And we're going to get 1 plus 6, and 5 plus 2, 7, 7. All right. So W2 can be any number, right? Yes, that's true. So to demonstrate, we could say, let's choose our eigenvector to be 2, 2, like that. And we would expect 7 times that number, 2, 2. So if I had chosen W2 to be 2 instead of 1, I chose it to be 1, then this matrix is going to be 1, 6, 5, 2 is going to times 2, 2. We'll get 2 plus 12, and then 10 plus 4. So we'll get 14, 14, which is 7 times 2, 2. Yeah, so the eigenvector can take many forms, but there is like one simplified eigenvector, I guess you could say. But the eigenvalue is one specific number. In this case, the eigenvalue is always 7. But you could have like the eigenspace that corresponds to this vector is all vectors that look like this. So it could be any multiple of the vector 1, 1. So all of these are the vectors that make up the eigenspace corresponding to this eigenvector. Did I make a mistake? For example, 2 shouldn't have AV. I might have done it wrong. I'm trying to move too quickly. Negative 12 and then 3. You are right. This should have been a 9. I think it's still, since there's an 11 there, I think it still is bust. So it's still not an eigenvector. But yeah, you're right, Janice. Thank you. Good catch. Okay, I'm trying to keep moving at a good speed here so that we can get to the other section. And this section's not too hard, so I'm hoping that it's making sense. You guys seem to be giving good feedback. So let's have a look here at example 4. They give us a matrix A, and they tell me that A has an eigenvalue of 2. And then they say, find a basis for the corresponding eigenspace. So a basis for the corresponding eigenspace means what vectors, or maybe vector or vectors, span the space corresponding to that eigenvalue. So let's find the eigenvector that corresponds to it. So we want AV, so V is the eigenvector that we want to find, equals 2V. So apparently there's a vector out there that when you multiply it by this matrix A, it just doubles it. That's all it does. So we want to find that vector on which that happens. So let's subtract the 2 over to the other side, the 2v, factor out the v, oops, factor out the v, so we get minus 2 identity matrix, v, and then A looks like this: 4, 2, 2, negative 1, 1, negative 1, 6, 6, 8. And we want to subtract the identity times 2. So the identity, 3 by 3 identity, looks like this: 2 on the diagonal. V equals the 0 vector. So it looks like that. So what we want to do is subtract 2 from the main diagonal. Oh, that's cute. And augment that with the 0 vector and row reduce. So we're going to have 2 free variables. That's a 6 there. So we have 2 free variables. v2 is free and v3 is free. So what that means is the eigenspace that corresponds to, or the eigenvector, the eigenspace that corresponds to this eigenvalue is of dimension 2. We're going to have 2 vectors that span the eigenspace. So let's see here. So v is just v1, v2, v3, and v1 is 2v2 plus minus 6v3, and then v2 is free and v3 is free. So let's bust this up according to v1 and v2. So it's going to be 2, 1, 0 for v2, and it's going to be negative 6, 0, 1 for v3. So these are the 2 eigenvectors. So the space, we could say eigenspace corresponding to lambda equal 2 has basis two, 1, 0, negative 6, 0, 1. And there we go. So if I multiply either of these 2 vectors to A, it should just be doubled. The vector will double. So it's all it really does. So in some sense, we're finding the fundamental, like, what is this transformation doing? What is this transformation doing? And we can say it is, if your vectors look like these, the transformation is just doubling. So we're reducing the entire matrix multiplication down to just scalar multiplication, which is really easy. So scalar multiplication, you just double the vector, and multiplying matrices is harder. So we're trying to find, again, some root idea here. Let's see, did I make a mistake? Let's see, 1/2 v2 and negative 3. Oh, you are right, Daniel, you've got me. Since this is not a 1, I have made a mistake here. So these vectors need to be divided by 2. So now, are these still eigenvectors? Yes, they are. But I did make a mistake there. So this should be 1/2. So you could put a 1/2 out in front of these, or you could just choose v1 and v2, or v2 and v3 to be 2. If I choose those to be 2, then these still cancel. So I got lucky. My eigenvectors are still the same, just because I chose a scalar. So we can double check just by multiplying them if you would like. So let's go ahead and do it. 4, 2, 2, negative 1, 1, negative 1, 6, 6, 8. But that was good to point out that I did make a mistake there. I forgot to divide everything by 2. So we'll take, say, this first vector here, 2, 1, 0. And then take the product. You're going to get 8 minus 1, that's not 0. We're not expecting 0. We're expecting 2 times the original. So this is going to be 8 minus 1 is 7. Uh-oh, I'm in trouble. Let's see. taking the product right. I only divided the first row by 2. Not the whole vector. Oh, I see. Um, yeah, I've boogered it up. Oops, I've boogered it up. So let's see. Um, thank you, thank you. So this is going to be, if I add that over, this is 1/2, and this is 3. Yeah, you guys have got it. So then what that changes these vectors to, I think what Caroline has posted there is correct, I believe. So then this is going to be, um, if I fix this properly, V1, or V is going to be equal to 1/2, 1, 0, V2, and then -3, 0, 1, V3. And so if I choose V2 to be 2, then the vector is 1, 2, 0. Yeah, which is what Caroline's posted there. And then the second one, we'll just do -3, 0, 1. So yeah, I was incorrect there. I'm glad I checked it. And I had you guys, or else I wouldn't have caught it. So here, let's just double check. We'll use this vector. Then we get 4 minus 2 is 2. 2 plus 2 is 4, and then 0 on the last one. So 0, and so then we end up getting 2 times the original vector. Yeah. Okay, good work. You guys seem to know your eigenvectors and eigenvalues pretty well. Well, that's good. Thank you. Good. So let's keep rolling. So let's see. They say find a basis for the eigenspace. That's what we did. It's of dimension 2. If you noticed in the animation that we saw in the beginning, right here, it's not just a coincidence that the eigenvectors are perpendicular here. So the eigenspaces will always be perpendicular. So the normal to this plane that's spanned by those two vectors is going to be the third, or the other eigenspace. So we have 2 eigenspaces here. So these two generate this flat plane, and then the normal to that plane is going to be the other eigenspace. Okay, well, let's look at this next one, example 5. They give me 2 matrices, A and B. They say find the eigenvalues for A and B. So we need to actually go back and look at our notes. -3. Did I make a further mistake? I think you are right. I didn't take the time to... Let's see. So I divide that by 2. I think this is correct, Caroline. The one there. If you want, we could double check that one. So if we double check by putting -3, 0, 1 here, and then just multiplying it through just to be sure, we get -6. -6 minus 6 is 0. -6 is 2. Yeah, so we're fine. So I think this is correct for this one. Yeah, thanks for checking though. So let's go back and look at our notes here. So there's a really handy little theorem here. If you happen to have a triangular matrix, So that, remember what triangular matrix is. That means all the values above the main diagonal are non-zero. Well, not necessarily non-zero. All the elements below the main diagonal are zero, and everything above is either zero or non-zero. So if you happen to have a triangular matrix, then the eigenvalues are the elements on the main diagonal. So you can just read them off. So let's go have a look at example 5 again. Here we happen to have two triangular matrices. So the eigenvalues here, lambda 1 is 3, lambda 2, 0, lambda 3 is 2. So I'm just looking at the elements on the diagonal. These are the eigenvalues of a matrix, of this particular matrix. 4, 1, and 4, so there you go. So we have lambda 1 is 4 and lambda 2 is 1. So you don't have to say lambda 3 because you already have this eigenvalue listed. So these are the eigenvalues. Now the question that you should be asking here is, what if I were to start doing row operations? Like what if I were to divide this by 2? Well, then does that change the eigenvalues? And so the answer is yes. So we want to know what changes the eigenvalues and what leaves them the same. Do row operations in general change them? And the answer is yes to that, because I could just divide this row by 2, and then boom, immediately lambda equal 2 would be an eigenvalue, and that's not the case here. So let's go ahead and look at the next section. How are we doing on time? Okay, not too bad. So that whole last section, we didn't look at how to, if you were observing well, we did not look at how to find an eigenvector. We only found eigenvectors if we were given eigenvalues. So then the question is, how do you find eigenvalues? And that's what this next section is about, finding eigenvalues. So my last little question down here says something, I don't know if you have the printed notes out for this, but it says something about discovery of eigenvalues. Matrix must be singular implies that's 0. So this means that Mr. Margraf didn't finish the notes last year. So what I need to do here, so this is what we want to find the eigenvalues here. So how would we do that? Well, we want solutions to this equation. We've seen it before. We want the solutions to this equation. Well, we want non-zero solutions, so non-trivial solutions. So what that means is we want the determinant, we want this to be non-singular, because if it has a free variable, so we want no free variables. And no free variables means that it's invertible, which means that this is not 0. So we want to find out when this has when this matrix A minus lambda I is singular. And if we can find that, if we can find the lambda values that make that true, then we've found the eigenvalues. So we want so in order to be invertible, this would be non-zero, and so so we're looking for, I guess, a better way to say it is vectors that make this true, and if that's the case, then we're looking for eigenvalues that satisfy this equation. So on this page here, we're adding a few things. The determinant is just the product of the eigenvalues. So if the matrix is invertible, it's 0. And we also saw this, so we saw this theorem in chapter 3. We saw that if you just take the product of the main diagonal and the number of pivots, or the number of times you had to do row interchanges, multiply that by a negative, then that gives you the determinant. But now further, this is just the product of the eigenvalues, is really all it is. So the determinant is the product of eigenvalues. So I guess if you have something like 6 as your eigenvalue, or as your determinant. So say the determinant of a matrix is 6. Well, then these are really your choices for your eigenvalues. You could have 2 and 3. You could have 6 and 1. So that is really what your choice is. Now, some of these could be negative, right? So you could have alternating signs or something like that. But so anyway, that's the product of your eigenvalues. So we can add some things to the invertible matrix theorem. If 0 is not an eigenvalue, then it's invertible. If the determinant is non-zero, then it's invertible. So these are the two things that we're adding to our invertible matrix theorem. Let's see, I want to get to the characteristic equation. I'd love to spend more time on this right here, and I think we're going to look at it some point, but we just don't have the time. So let's go ahead and look at this definition 522. So we have this equation. This equation here is called the characteristic equation, and the solutions, or the roots of this equation, are the eigenvalues. So we'll say roots are eigenvalues. Okay, so let's see if we can go ahead and do an example of that. So find the eigenvalues of this matrix A. So here we go. So let's go ahead and first say A minus lambda I. Let's find that. That's going to be 2 minus lambda, 3, 3, negative 6 minus lambda. And now let's take the determinant of this. So the determinant of A minus lambda I. And we want to set it equal to 0. So that's going to be the product of this diagonal, 2 minus lambda, with negative 6 minus lambda, minus the product of this diagonal, which is 9. Let's do some expanding. So we're going to get lambda squared plus 4 lambda, and then minus 12 minus 9. Then we get a minus 21. Factors of 21 that add up to be 4. That would be 7 and 3. Three should be negative. So we have two eigenvalues. Lambda 1 is 7, negative 7. Lambda 2 is 3. So this is what we were missing in the last section. We didn't know how to find the eigenvalues. And so if we had the eigenvalues, we could find the eigenvectors. We went through that process. But now we're able to see the process here of actually finding the eigenvalues. So this right here is called the characteristic equation. Characteristic, I'm not sure if I'm spelling that right, equation. In the roots of the characteristic equation are the eigenvalues. Okay, so every matrix has a characteristic equation, and those roots are its eigenvalues. So let's see if we can do another one here. Why does it just want me to compute the determinant? I think they're having me do something. I think we're supposed to go back and read some of the notes here to do that problem. So here, we saw this theorem right here. If you do a row interchange, so I think that's what they want us to use in that example. So let's go back to that problem and do a row interchange. Let's see, if I do one row interchange, can I make it triangular? I don't think I can. So the determinant of A, we'll use the vertical bars. And then let's maybe interchange a couple rows. We'll put this one in the center. And so by interchanging the rows, that puts a minus out in front of the determinant. So it alternates signs by interchanging rows. This is not quite diagonal, so um, I can't just do the see, I feel like I'm missing one of they're probably trying to get me to use one of these particular problems. Yeah, maybe that's what we're trying to do. Trying to use one of these properties, I'd imagine. Um, the reason that we're doing more with the determinants here is because you have to use the determinant to find the characteristic equation. And so we want to get proficient at finding determinants, which takes effort. So here, let's see if I can... yeah, I'm not sure if we're doing the transpose. So, yeah, so what I'm going to do instead is just go ahead and do the same thing that we've done before. So I'm going to expand about this last column, which means that I'm going to eliminate this row column like that. And so we have, this is -1 to the third row, third column, 3 plus 3 times -1, determinant of the deleted matrix. So it's been a while since we've seen that, but that's the idea. So we have negative, negative, the determinant of this matrix is just going to be -2. I'm not sure what I was supposed to learn from that problem. I'm assuming that they want me to use one of these properties up here that we are learning. Um, Product of the determinant is, or the determinant of a product is the product of the determinants, and these are just really a review theorem. I mean, we've already spent time on this before. We even proved this one, if I recall. Um, let's see. Yeah, and we're just adding these two on, I think, is what we've done. Okay, well, let's keep going. Let's see, what was that? No, similar matrices. We don't really have to look at that yet. Okay, so let's go ahead and look at example 3. It says find the characteristic equation, so let's get to it. So we are pretty much out of time. So let me do this one last example, and then I think we'll probably call it there. I really wanted to get to the characteristic equation, and that's at least what we've seen one example of. So let's try this one here. So we want a minus lambda I, and we want the determinant of that. So it's going to look like the determinant of 5 minus lambda 0, negative, so this is 3 minus lambda, uh, 5 minus lambda, and 4, and then 1 minus lambda. So now to find the determinant, you just have to multiply the diagonal. So this is going to be 5 minus lambda, 3 minus lambda, 5 minus lambda, and 1 minus lambda. And by setting this equal to 0, this is the characteristic equation. So what are the roots? Well, you can see that lambda 1 is 5, lambda 2 is 3, and then lambda 3 is 1. So 5 occurs twice. It's multiplicity 2. So that implies that the eigenspace that corresponds to it is also 2. Let's see if we can... yeah, so I think we're going to call it there. This was a shorter section, so I was hoping that I could try to cover most of it. I think what we're going to do next time, our last class together, is I'll probably spend a little bit of time talking about what similar matrices are, and I think that's where we'll start the algebraic multiplicity characteristic equation. So there's a geometric multiplicity and algebraic multiplicity. So the geometric multiplicity is less than or equal to the algebraic multiplicity. So I think I misspoke uh, on this particular problem right here. Since 5 has algebraic multiplicity 2, its geometric multiplicity, geometric, is going to be less than or equal to 2. So it could be 2. It could be 1. So it's the dimension of its eigenspace is of maximum value 2. So anyway, we'll hopefully look more at that next time. But I think next time we'll probably start with diagonalization and talking about similar matrices a little bit here. And I'm happy to get through diagonalization. I think that's good. We're pretty much ending chapter 5. Chapter 5 has I think maybe 1 or 2 more sections that I usually like to cover. But I think ending with diagonalization is a good point to end at. In some of my linear algebra class in college, my undergraduate, it ended with quadratic forms, which is a little bit later. It's in chapter 6. So I think it's maybe like 3 sections away. So I'm not too disappointed if this is the farthest we get. But if you would like to go further, I do have some resources that I can direct you to. So I think I will do that next week. So if you're interested in doing some summer learning on this topic and kind of learning the rest of the course, I'll give you those resources next week. But I think we'll end the video there.